Okay, ladies and gentlemen, we are now going to look at Unit 4, Lesson 2. How does it change? So we're going to look at dot patterns, and we're going to study the patterns. And our first question was, how are the numbers of dots changing? Well, in looking at these, it might help to count them. In step 0, we have 1 dot, and then 3 dots. Here, I see 5 dots, and then 7 dots. So overall, I can see our rate of change. We are continuously adding 2. And then at step 0, I start with 1 dot. So we actually know, because I'm continuously adding 2, that this is linear. In the equation, y equals mx plus b. M is 2, because that's our rate of change. So we can write an equation, y equals 2x. And then at 0, I start with 1 dot, so plus 1. So to describe pattern 1, start with 1 dot and add 2 each step. Now, pattern 2 is very different. So we start with 0 dots, and then we start with 1 dot, and then 4 dots, and then 9 dots. And as I look at this pattern, I notice something in the shapes. So 4 is a 2 by 2 square, or I could write that as 2 squared. And 9 is a 3 by 3 square, and I can see that as 3 squared. And 1 actually is a square itself. I can write 1 as 1 squared, and 0 dots is actually 0 squared. So looking at that, I can say for pattern 2, the dots are growing by an n by n square. So I can just say the dots are growing in a square. So to find the 5th step in each pattern, so I'm going to do pattern 1 over here. And for pattern 1, we actually have an equation. For the 5th step, we would say x equals 5. And in our equation, we would say y equals 2 times 5 plus 1. Multiplying 2 times 5, that gives me 10 plus 1, or 11. So I'm actually going to fill that in down here. And then pattern 2, we could also generalize an equation. I know that y, the number of dots, is equal to whatever the step number is to the 2nd power. So if I did that and called x the step number, y would equal x squared. So for step 5, y would equal 5 squared, which is in fact 25. So I'm going to fill that in down here. So for pattern 1, for step 1, I can plug that in and go looking at that, or step 0, I'm at 1. And then we have these. We have 3, 5, 7. And then for step 4, I can see that I'm adding 2, and I'm just going to put 9. And then 11. I almost want to just continue that pattern and put 13, but I notice I'm at step 10. So I'm going to have to substitute into the equation and go 2 times 10 plus 1, which gives me 21. In general, for n, we would go 2 times n plus 1. For step 2, we would do 0 squared, which is 0, 1 squared, which is 1, a 2 by 2 squared or 2 squared, which is 4, 3 squared, which is 9, 4 squared, which is 16, 5 squared, which is 25, 10 squared, which is 100, and n squared. Moving on to graphing both patterns. For the first equation, it was y equals 2n plus 1. So 2 times 0 plus 1 would put me at 1. 2 times 1 is 2, plus 1 would be 3. 2 times 2 plus 1 is 5. 2 times 3 is 6, plus 1 is 7, so step 3 is 7. 2 times 4 is 8, plus 1 is 9, so at step 4 we have 9. 2 times 5 is 10, plus 1 would bring me to 11. 2 times 6 is 12, plus 1 is 13. And then it wouldn't make sense to connect the dots because there are no step 1/2 and then so on. But I notice that this pattern is linear. And then for the other graph, we could say 0 squared is 0. 1 times 1 gives me 1. 2 times 2 gives me 4. 3 times 3 gives me 9. 4 times 4 gives me 16. 5 times 5 gives me 25. And 6 times 6 is off the graph. For the second graph, I'm going to connect those dots to make a line, even though it wouldn't make sense to have a step between 1 and 2. I'm just going to connect them to show the difference between them. Now we're going to look at a little bit of a different pattern. And we would say, is a number of small squares growing linearly? So to determine that, I'm going to look at the rate of change. So first, I need to count the squares. So step 1, we got 3. And then step 2, 4 here plus 2 there is 6. Step 3, 3 by 3 is 9, plus another 2 is 11. As I examine the rate of change, I notice that from 3 to 6, I add 3, and from 6 to the 11, I add 5. Since 3 and 5 are not the same rate of change, it is not linear. So the growth is not linear. Because the rate of change or the slope is increasing. So we'll just say because the rate of change Now, to try to complete the table, I see we have 3, and then 6, and then 11. So one thing that I notice is at first I added 3, and then I added 5. I think the rate of change might be increasing by 2, so I'm going to think I might add 7. So I'm going to draw step 4 to verify that pattern. And for step 4, I know that I'm going to have a 4 by 4 square with 2 on the ends. So if I count that, that's 16 plus 2 gives me 18. and 11 plus 7 is 18. So on here, I know I would add 9. 18 plus another 9 would give me 27. However, I can't keep doing that because I go from step 5 to 12 to n. So I'm going to have to look for other patterns. Now, I know this is not linear, so I'm wondering if this growth is quadratic. I know that quadratic functions have squares in them. And I can see here, I have squares. So here I have a 2 by 2 square, or 2 squared, and then I add 2. And that does, in fact, give me 6. For step 3, I have a 3 by 3 square. So we have 3 squared plus another 2. And for step 4, we have 4 squared plus 2. And it looks like I have a pattern. Whatever the step number is, I square it and then add 2. So for 10, I'm going to do 10 squared plus 2, which would give me 102. For 12, I would do 12 squared plus 2. 12 squared is 144, plus 2 is 146. For n, I would go n squared, and then I have my 2 on the sides. So is the number of small squares growing exponentially? No. The growth is quadratic. As we look at our expression, the relationship between the step number and the number of squares is quadratic because n squared plus 1 is an example of a quadratic expression. Anytime n is to the second power, it is quadratic.